So, nice to be here in Pamplona. I've been many times in Spain, many regions, but never here. So it's a good thing to do. And there's also a good reason, which is to try to tell you about some of the work which is going on in an area which one calls chemistry. And people often say, I don't like chemistry. I don't understand anything about chemistry. That's a big mistake, because you are all chemistry. You are chemistry. You wouldn't exist without chemistry. But in order to introduce this, let me start, first of all, to tell you about the title, of course. Steps towards life, just steps. We don't know exactly where we will reach it, when we will reach the final steps to understand it, but it deals with chemistry. In order to understand that, we have to start very early on, just to see where chemistry comes in. Very early on means the Big Bang, 13.7 or something like that billion years ago. At that time, there was only energy, no chemistry. It was much too hot. Then the universe, after the Big Bang, started to cool down quite quickly. Particles formed. Particles came together to form nuclei, atoms. That's the age of physics. No chemistry. When it cooled down further, atoms could bind together to make molecules. And then chemistry started around here, 300,000 years after the Big Bang. That's the age of chemistry. Now, it didn't stop there. More and more molecules were formed. They began to aggregate. They formed populations of molecules. And at some stage, a property appeared in this soup of molecules, which we call life. As I said, we don't yet understand all the steps, but we know at least that it's happened about here. Life started, it's the age of biology. But it didn't stop, at least on our planet, and very probably on other planets too. Another property appeared, much more important than life, for me, which is thought. Without thinking, we would not be here. We would not even talk about life. And this is steps towards life. The thinking I have represented by a famous sculptor, of Auguste Rodin, the thinker. But I didn't mention it for that. I put it at the end of the screen because that is where we are. But let me just tell you that the universe will continue to evolve. And when we see environmentalists and people like that who try to stop things, this is totally impossible. And if we try to stop it, the universe doesn't bother. We will be wiped out. So what? I think there is no way to stop evolution in the universe. It will continue. And we better go with it. Now, it looks like a slide with nothing on, but there is something. There is dark energy and dark matter. The cosmologists tell us that that represents 95%, which is darkness. For the moment, we don't really know what it is. 95% darkness. But there's 5% visible matter. That's our matter. That's the matter that matters. That is ours. The cosmologists even exist only because there is visible matter. And they can dream of dark matter only because there is visible matter. Now, this evolution of matter has started by being divided particles. Then it became condensed, making atoms and molecules. Then it became organized in some way. Then it became living in some way. Then it became thinking in some way, many some ways here. And maybe something else may happen beyond. Very difficult to know what exists beyond our own thinking, but we cannot exclude it. And that is a sort of way towards more and more complex states of matter. Now, then we have to ask a very big question. I think the biggest question we can ask. What is it? Simply, how does matter become complex? How can we come from an elementary particle to a thinking organism? And are there even higher forms of complex matter? That's a fundamental question. The type of organisms on this planet, us, invented a methodology to try to understand, to give an answer to this question mark. For that, mankind created science. Science, if you look only at three domains of science, physics deals with the laws of the universe. These are the fundamental laws on which everything else depends, and all the other fields depend on that. These are the fundamental laws of the universe. Biology deals with the rules of life, not laws, that's just rules. The laws are the basic laws of the universe. So what is chemistry doing in this? Is trying to build a bridge. How can you go from very general laws to a specific expression of these laws? How is it that from these general laws you can make something like an elephant or a human being or something else? Now, the answer to the question, in fact, I can tell you what it is. You will be surprised because you say, okay, if we knew the answer to that question, it would be in all newspapers, everywhere. Maybe it should be. The answer is self-organization. In other words, it happened because the structure of our universe is such that it will produce order. That's a strong statement. We exist because the universe made us. It's a tautology. Huh? We exist because the universe does it. So there must be spontaneous organization of visible matter in our universe. We can even claim that it is a cosmic imperative. That is given even, we could discuss that at dinner. There's even going further to say that life is not an accident. Life is a product of our universe. One man can dispute it, but I can also claim it. Now, before there was life, and we heard yesterday a fantastic lecture on biological evolution, Darwin, fantastic what happened. But before biology evolved, there was an evolution which was pre-biological, which had nothing to do with living organisms, but which was in line with the living organisms. In other words, there was a purely non-living evolution which progressively generated the steps and then the threshold where life could appear. You cannot, or you can, but it's very difficult to imagine, to accept that there was one jump from a particle to a living organism. So it built up progressively. So, at least for me, self-organization is the driving force of our universe. So in this concert of scientific fields, I didn't mention the other ones. Sorry, I didn't mention botany. I didn't mention many others. But chemistry is considered as the science which deals with the structure of the universe, of matter, how it is built, and the transformation of matter. How can you transform given entities of matter, let's say molecules, into other ones? That's why I'm a chemist, because chemists can take a bunch of molecules and make another bunch of molecules. That's Promethean. You have a power of the intrinsic structure of matter. Of course, physicists can do it also for other reasons and in other ways. So, yeah, let me elaborate a little bit on this. The structure of matter. Matter is formed of pieces, of bricks. These bricks, along the years, scientists found out that there were small pieces which one cannot make smaller, atoms. Democritus was the first one to call that atoms. Atomos, cannot make it smaller. And these atoms were sort of chaotic until the middle of the 19th century, when a few people, but especially one of them, noticed that you can put order in all that. And this was the best known, and the one who went farthest was Dmitri Mendeleev. In 1869, he published what I consider as one of the most important papers ever in science. This is the original paper, written in German, in Zeitschrift für Chemie, 1869, where Mendeleev noticed that one can make correlations between properties and atomic weights of atoms, and to produce a table shown here. Furthermore, he noticed that in this table there were empty places where he put a question mark. And this is important in science also. When you are sure enough of what you do, you make a step and say this will happen. You predict. And of course, he was right. This happened. Nowadays, of course, the table is more complete, and that is what... Sorry, I should first mention that also this year is the 150th anniversary of this famous paper. It was celebrated all over the world, everywhere. Now, this is now the table. In fact, you have it big scale in front of the building. Huh? Yes? That's fantastic. I had never seen that before. I know there's a periodic table of the elements on the wall of one of the universities in St. Petersburg. Nicely painted on the wall. But this is the biggest one I've ever seen, and the heaviest one I've ever seen. But it's very nice. It's fantastic to show that people. Because this thing is, as I said, the most important thing I can think of for us. Because it shows you the elements, this periodic table, it shows you the elements which make up matter, our visible matter. And they are all present. There are no other ones, except, of course, the artificial ones down there, but I'm not interested in that. And why are they? This is a bit strange. A scientist shouldn't be dogmatic. You cannot be dogmatic if you're a scientist. But here, I have to accept, you have to accept, that the table is complete. It's full. And simply it's full because it's like counting. 1, 2, 3, 4, 5. 1 proton in the nucleus, 1 electron outside. 2 protons, 2 electrons, 3, and so on. 1, 2, 3, 4, 5, 6, and so on, until 92 uranium. So, it's full. There's nothing between 1 and 2, between 2 and 3, which means also one thing, which is absolutely, I mean, it's incredible that we know that. If there is a living organism or any kind of life anywhere in the universe, billions of light years away, they have to be formed by the same elements. There are no others in our universe. So look, this is what I tell when our experiments go wrong, when things don't work. You look at the periodic table and say, we did something. No, really, you know, this is incredible to sit in front of this table and to say that we know what visible matter is made of. And that is what chemists play with. Chemists are like children. They like Lego. The Lego pieces are the elements. They have certain rules of combination, and out of that, you build, you build, you build, you build. Like with a stone, you make all kinds of buildings. So, from the atom then, building up molecules, molecular chemistry developed. Let's look just very, very briefly at sort of a milestone which gives us some idea. These molecules are formed by taking these elements, forget about this, no, for the chemists here, covalent bonds, they know what that is. Strong bonds between atoms allow the constructions of molecules. Okay? Now let's look at 2 milestones. First of all, in 1828, a German chemist, Friedrich Wöhler, made urea from another chemical called ammonium cyanate. Urea is contained in living organisms, urine. Ammonium cyanate is an inorganic one, is something which is not organic, not in an organism. So, first of all, Wöhler was happy to be able to transform ammonium cyanate into urea. Okay, that is what chemists call a synthesis, making a new chemical object from the previous ones. But it had also a very profound, I would say, metaphysical, philosophical effect, because at that time people were thinking that you could not make in the laboratory, in a synthetic way, artificial way, anything contained in living organism without the use of a magic force called the vital force. By making urea from ammonium cyanide, Wöhler destroyed this idea of the vital force. And he knew that he had done that. So there's a continuum between the molecules of non-life and the molecules of life. Now, 150 years later or so, this huge molecule, vitamin B12, which you have in your blood, was made in the laboratory from its elements, carbon, hydrogen, oxygen, nitrogen, and there's a little bit of phosphorus there. There's some P, phosphorus, and there's there's a P here also. Huh? And cobalt, and so on. So this is a big thing, and it took many years. It took the collaboration of two groups, one directed by Robert Burns Woodward at Harvard, and the other one by Albert Eschenmoser at the Polytechnical University in Zurich, collaborating transatlantic. At that time, there was no email, so one had to send letters, one had to send packages, and so on. And helped by about 120 men and women among the years who collaborated. And I was postdoc with Woodward, and this is my piece here, that here. So, you know, this is also to show for those who want to do science. When you do science, you know that you are part of a big scheme. You have to be modest, but you know that you are there. And your piece, nobody will take it from you. And that is why also I claim that when people say by being creative, creating things about an artist, a chemist creates the same thing, but much more deep inside matter, not just the surface. So this was in the 70s of last century. Of course, molecular chemistry developed much more. And nowadays, you would not make B12 the same way it was made at that time. So molecular chemistry is strong, studied everywhere, in Spain, everywhere, and it continues. But then you can ask a question, and let me introduce it in the following way. Here we see a cancer cell and two bodies which are called killer cells. Killer cells are the police in your body. You have them here, as you sit here. They run around your organism, and they have a job, very important. They have the job to find out what has gone wrong. They have to find the cells which have gone bad, transformed, cancerous, and to destroy them. So how do the killer cells know that? If they make a mistake, they are in trouble. Either they destroy a healthy cell, no good, or they don't kill a transformed cell, no good. This is an image of HIV virus infecting a white blood cell. The HIV virus, when it hits a white blood cell, it can penetrate, infect. How does the virus know, if I may say so, that it has reached the target? So these objects are, of course, defined by a membrane. They have a given shape. They have a membrane. This membrane is made like a soap bubble, so kind of very, very loosely, so kind of thing. And in this membrane, which looks like a little bit like a soap bubble, there are other molecules inside, proteins molecules, which characterize what these cells are. So it is by touching one another that the killer cells know that the other guy is either good or bad boy. And this then opens the possibility to study this and to try to understand the next step in complexity in matter. What do molecules do when they get together? Molecules are usually a population, and this population interacts, and that is what happens here. The molecules on the surface on these membranes interact with the molecules on the other surface. And that tells the killer cells the other one is or is not a cancer cell. So that's a chemistry which now lies beyond the single molecule. It's a chemistry which is a sort of, let's call it, a chemical sociology. Molecules can hate each other, can love each other, can transform each other. And, okay, forget about how it happened to us. And three main functions have been studied over the years. How do molecules recognize each other? How can they react with each other? That means transform one another. How can they carry one of their colleagues through a membrane, a barrier? And this was what has been studied for many years. And the most important is molecular recognition. How and what is the basis of molecular recognition? I would insist on one thing, that molecular recognition is the basis also of life. You cannot, without molecular recognition, you don't live. Molecules have to know what to do, when to do it, at what rate to do it, in which place in a cell to do it. So all of you depend on the way in which molecules can fit together and recognize each other. So let's give an image of this recognition. Molecular recognition, therefore, needs, first of all, a gluing interaction. They have to feel each other. Right? If you don't feel, you ignore. So there's a feeling between them, and there are physical interactions between molecules. That's number one. But the most important characteristic which we have to add is that there is information. You cannot recognize if there's no information. So molecules carry information. Any molecule is an information carrier. And you can, very simply, the simplest way is to say that there's a sort of a complementarity in geometry and in interactions. You may know, of course, that plus attracts minus, plus repels plus, Coulombic interactions. That's the level 0, but it is already good enough. And especially in 1894, a German chemist already formalized this notion. He didn't call it molecular recognition at that time, but he worked on a way in which enzymes, molecules of biology, transform their substrates into products. And in order to work, they have to have a property which he calls a complementarity, fitting together like Schloss und Schlüssel, like a lock and a key. This person was Emil Fischer. He wrote this very famous paper in 1894. And let me just also make the remark I'd like to make. He got his doctorate at our university in 1874. He was a German. We were German at that time. Because after the Franco-Prussian War, lost by France, Alsace and part of Lorraine was incorporated into the German Empire. So we were German. I mentioned that just to say, now we must all be Europeans. Okay? Now, the most important and impressive way of information storage and later on processing is a very simple molecule chemically. Chemically, it's much simpler than vitamin B12. It's much bigger, but it is simpler. Simpler because it just consists of a long chain, a chain of entities bound together, and on this chain you graft letters. The letters have received names. Chemists play with these awkward names, you know, adenine, guanine, thymine, cytosine. They call it also, could have called it ABCD, would have been the same. It's just, it happens that it is called this way. And these groups here, for a chemist, are rather trivial, very simple compared to vitamin B12, for instance. But these four letters write the genome of all living organisms. Between a tomato and an elephant, it's the same letters, just another sequence. This is also quite incredible. So we are the result of just four letters, a specific sequence, of course. Before I continue, let me analyze one of those letters very briefly. Adenine, in fact, can even be reduced to something more simple, very simple. It is a polymer, that means it's 5 molecules of HCN, cyanohydric acid, which form around, they pentamerize. 5 of them go together and form this. You see here, you have HCN. It's a bit rearranged, but HCN, there are 5 HCNs there. HCN exists in interstellar space, so adenine can exist in interstellar space. You add some water, which also exists in interstellar space. You can make guanine and some other rearrangements. You get the other two letters. So, in principle, not big deal, no big deal. So this is the way to store information, the sequence of letters. But then this is not enough. You have to be able to read it. The reading is also trivially simple. It is just touching. It's pairing up. Two of these letters, called adenine and thymine, or uracil, it's a slight modification, they interact by 2 points of interaction, which are represented by the little dots here, these dots. The other 2 by 3. So the difference between the 2 is very simple. 2, 3, 2, 3. A computer is 0, 1, 0, 1. It is 2, 3, 2, 3. So if you have a long string of these 4 letters, you can pair them up, and that's the way the genome is read. And then, of course, development of an organism is very, very, very complicated, but that's the first step. That's the conservation of the information and the reading of the initial information. Now you may say, come on, this is not possible. It must have been tried more. Why only 4 letters and 2 ways of reading? Why not 10 and 6, 10 and 5 ways of reading? For 2 reasons, probably. 1, 4 letters and 2 pairings is enough. You don't need more. And if you have more, it's richer, but it's probably quite chaotic. Very difficult then, huh? Because you have to read it. Even it's known that there are correction mechanisms and so on. So probably the most efficient way to allow for the generation of life was to keep it simple. Don't make it more complicated than you need. I think that is usually in science also a good lesson. Huh? Don't complicate things more than you. Like I think Einstein said, you should make things as simple as possible, but not more. So chemistry, therefore, is also an information science. It's a science of informed matter, where the molecules store the information, and the supramolecular level, these interactions, they process it, and this is then probably the most important contribution of supramolecular chemistry to the way you perceive chemistry. So then chemists have started all over the world playing with locks and keys. I just give an example here. That's a keys. It's a lock which you can make, or maybe a natural one. And of course, the red key is the one which fits. So we like to play. Chemists like to play. They think, okay, how can I distinguish spheres from spheres, or tetrahedra from something else? So you design the key, the lock. You make it in the lab, and you see if it works. And then you learn more and more. And this has been done then in very many laboratories around the world. I have no time to get into details. But let me just give you some ideas about possible applications, because often people ask, so what are you doing? What is it used for? You're just spending time, you're spending money. What is it used for? What is the interest? So let me just, first of all, say that basic research gives you knowledge, and without knowledge, you have no applications. Like one of my friends, he's not the only one, said, if we had no electricity, we would have candles of all shapes and colors. But no, these light bulbs. So basic research is what is at the bottom, out of which you can have nice flowers of applied research developing. So the most important application of this story is in making drugs, pharmaceuticals, because a pharmaceutical object, a drug, is a molecular key for a molecular lock, a biological lock. And that is the way drugs are made. That is what's called drug design. And this is the most important application, because when you know how they interact, you can try to design the correct drug. Other things which we have done, but I want just to mention it, is that you can also produce ways of analyzing, for instance, for thicknesses, for diagnostics, labels, and so on. And that is one example of a machine which was made for making diagnostics using immunoproteins. Then another one is to transport, as I said, through a membrane. And this can be applied to a specific field, which is flowering, which is Gene transfer. Gene transfer is very important, on one hand, for gene therapy, correcting genes which are deficient, for instance, for children which have mucoviscidosis, which have a disease which is a very strong, a bad disease. But it is also, so gene therapy is developing quite well now. It takes a long time to develop these kind of things. But also for biotechnology. Biotechnology, what I mean by that, introducing foreign genes into a given cell. This is called making genetically modified organisms. Those have a very bad reputation. I think it's totally wrong to give them a bad reputation. We need genetically modified organisms. We will make them, and nobody will stop it, even if you think you can. We need it. Especially if it really heats, as you said. You make plants which resist the heat. We make plants which take less water. Also, photosynthesis, this fantastic process, is very inefficient. Very little of the sun energy is transformed into the fixation of carbon to make plants. Let's work on these objects to make it more efficient. It's not simple, because many people have tried, have not succeeded for the moment. But anyway, the fact that you have not succeeded doesn't mean you cannot succeed. That's what drives us, isn't it? And finally, also, you can make biomaterials, materials which are a new type, and which just illustrate that in the following way. Biomaterials which can be made from these ideas of supramolecular chemistry. And let me just, and this is also an illustration of how long it can take. But it has to be patient. Scientists have, one thing they have to learn is to be patient. And if you deal with objects which grow 1 year and year and year, you have to be really patient. But in 1990, we published this idea of making polymers, that means plastics, so to say, of supramolecular nature. And then they were made biocompatible in 2013 by a small company, a startup, which developed supramolecular polymers, out of which you could make plastic units, like plastic covers and so on, which can be used for reconstructing the heart of children who have a congenital cardiac malformation. And here is the first little girl, Dominika, in 2013, on October 23, 2013. She was implanted by this Russian surgeon, a very well-known surgeon. I didn't know him, but now I know him. And they look happy, huh? Both of them seem quite happy. And so this was 3 months. So it was in December or something like that of 2013. And this has now been used for more children than that. And they've also developed heart valves, which have been implanted in Budapest, in Krakow, and in Kuala Lumpur. So this was something which took 23 years to come to an object, a device you can put in a body. Now it is known, of course, it's more easy to modify a computer because you don't touch a body. From the moment you touch a human body, it's very difficult. And sometimes even you could think that the fact that we want to protect us also makes us shoot in the foot. Because you make maybe too many protections and you miss a number of things. For instance, aspirin, which has the property of making stomach ulcers, if you are not careful, probably would have a hard time going through regulations now. Luckily, it was made in the 19th century. You have just to know how to use it. So let's go back to the main theme, supramolecular chemistry then. If you can understand better recognition, then you might also be able to use this knowledge to devise objects which will self-organize. In other words, we will generate out of bricks a complicated assembly of these bricks. I just show you examples to illustrate. It's a spontaneous process, but not just garbage, not just anything. It's a spontaneous process which you want to direct towards the formation of a given architecture. Now, in biology, of course, that exists. We are self-organized. We develop by progressive, very complicated processes, but a much simpler biological object which in fact is not living, because a virus doesn't really live. A virus is on the borderline between life and non-life. And this virus from the tobacco mosaic virus is made from 2,130 bricks, proteins, which go together spontaneously. And because of their shape, they're like a sort of piece of pie, and because of the surfaces which can stick to each other, they assemble and they build up this type of this type of tower, and in the middle there's a hole where there's a genome with a virus in it. This is spontaneous, and it's not magic. It looks like magic, but it's not magic. We know everything. We can understand everything that is there. It doesn't need any new theory. It's organic chemistry, physical chemistry, physics of interactions, and so on. So these are sort of a programmed system. A virus self-assembles following its own program. And this also means that in terms of using this kind of processes, it can lead to the possibility of making systems which will self-fabricate. This is ultimate fabrication. Let's an object make itself. That is, of course, important for nanoscience and nanotechnology. Let me just show you a few of those we made in our lab, but many people around the world are now making them, are making even more complex ones. One can make a double helix and a triple helix. Has nothing to do with a natural one. It's just a way to show that there are different ways of getting specific architectures. One can make a nice little grid where there are location of atoms at given intersections, and one can make this sort of cylinder where long molecules and flat molecules go together and are bound together, linked together by these little balls you see, which are metal ions, like zinc or copper or others. And this is just some other examples. So this can be made, and more complicated than those have been made, and people are very actively trying to understand how we control and how we can make successive steps in making more and more complex objects. So let me just show you one more step, which is important, especially since yesterday also we heard a lot about evolution, a fantastic lecture about evolution. What I showed you up to now is how you can design. You try to understand what's going on, you design a system, and you let it go. And then it should generate the object you want. And this is then a way of controlling, of generating in a controlled way molecular or supramolecular entities which have given functions. The next step is to let the system operate by itself. This is doing this chemistry with selection, setting up chemical systems which will choose out of a diversity of pieces the ones they need to build themselves up. This is the step of selection, where then you need diversity of objects because you want to select. You need dynamics. You need the objects not to be stuck together too strongly. If not, you are at the end, you are in a dead end. And this then leads to the idea that making objects whose chemical constitution is dynamic. That means it can fall apart and reconstitute themselves. Let me just give an example which makes it understood. You want to build a house. What do? You buy a truck of bricks and cement, and you build your house. And when you are fed up with that house, you dismantle it and you make another one. In other words, in this dynamic case, you can, out of the same pieces, make different architectures. Except here, of course, in the house, you have to do yourself, but in this case, in chemistry, you can then let it do by itself. This is now a process where also the assemblies will react to what happens outside in the environment, so they adapt, and this is the field of adaptive chemistry, which we are now mostly, it's our main line of research. Okay, so that's what I want to tell you about that. I have still a few remarks to conclude. So chemistry started as molecular, making molecules from atoms. Supramolecular, making larger assemblies from molecular pieces. Then getting it organized, controlling the organization, then keeping it dynamic so it can move, can respond, and not just be just like a block of concrete, and adaptive, reacting to the environment. And that is progressive steps towards living matter, but we are still far away. Living matter is very complex, which is in fact reassuring, because for all these people who start chemistry or science now, there's a lot to do. So don't be afraid, there's work for everybody. Let me insist on one thing, that chemistry is, I like to say that, I said it a little bit briefly in the beginning, it can create novel expressions of complex matter. The book of chemistry must be written, not only read. Of course, you want to read what is already around, but you can also make what is not yet around. And the score of chemistry can be, should be, must be composed and not just played. So chemistry has creative power, which again, I like to illustrate by taking Rodin again. The hand of the artist brings a sculpture out of a stone. The stone doesn't contain it. The stone is dead. It's the artist which makes it come out. And this is, with the bricks of matter, the elements, you can build an infinity of objects, and therefore you can call chemistry the art of matter. Now, this is not new. Leonardo da Vinci said a fantastic phrase, which is not easy to find. It took me time to find it, to find the origin. People knew that it was around, but I had to find where it was. And this was written in Italian, of course, but in English, where nature finishes to produce its own species. Plants, tomatoes, elephants, human beings, and so on. Man begins using natural things. What do we have? The periodic table, the bricks we have in our hands. In harmony with its very nature. These are the laws of physics. You cannot do something which is against those laws. You have to follow those laws. But the ending is fantastic, because Leonardo was a scientist, an engineer, and of course an artist. And the ending is very strong, to create an infinity of species, to make all the things which have not yet been made. Notice that another very important anniversary this year, 500 years of his death. So we had Mendeleev, we have Leonardo, not so bad for this year. Now a little bit, just some back into mythology. You may know, you probably know, that this fellow, a god, stole the fire from the assembly of gods and brought it to mankind. Here he's running away with the fire of knowledge and looking over his shoulder to check if the other guys are not running after him to catch him. But they didn't catch him, so we got it. And here we have it. Here he's showing it. But we cannot give it back. What you know, you know. You cannot erase it. So some people may say, oh, let's stop it, let's go back to the trees. We know too much. But I don't think that will work. And it's not an issue, it's not a good way of doing things. But we have to just to notice that we cannot give it back. We have to live with it. So our path leads us from the quest of knowledge to the control of our own destiny. We have now the power to do that. What's going on? Oh, yeah. So in the past, this information between generations was transmitted in this way here. Took some time, but it worked. In the present, that's a way to transmit information. I guess you recognize Michelangelo here. And the future. What will happen? Maybe this. Now, I don't mean by that we will only talk to robots, that we will only shake hands with robots. We'll shake hands with our friends and our people. But we will transform each other. We will transform us. And we are already transformed. You may have new lenses in your eyes. You have a cataract. You make a piece of polymer and you put it in, and it works. You have broken your hip. You have a piece of titanium. And what I then like to say also, suppose you Monsieur gets a heart transplant from somebody else. He cannot say his wife anymore, I give you my heart. It is not his. So we are just a piece of objects, but we have one thing important, that's what is up here. That's what makes mankind. And for this, of course, speaking about the brain, you must mention mathematics. Just one brief mention. Here is Monsieur David Hilbert, a very famous mathematician. He looks like a mathematician. He's buried in Göttingen. And here is his tombstone. On his tombstone, there are 2 sentences written there. What are they? He wanted that to be inscribed on his tombstone. First, top one, wir müssen wissen, we must know. And that's already strong, huh? That's strong, we must know. You can say, oh, forget it, I go back to the trees. And the second, wir werden wissen, we will know. That's a lot of confidence in what we are doing. It's some people who say it's overconfident, but I think that's what drives us as scientists. We must know, and some of us will make progress in knowledge, and eventually we will know more and more. And up to when, this I don't know. And here again is Prometheus with the fire and the light of science, and I would like just to ask you that, first of all, try to get enough, and you are here for that. So that is fantastic. There's not enough science because people try to react before they think. So try some science. People who do tennis, they are ready to play tennis a day a week. Why not take 2 hours science a week? So participate, and since science will shape the future of humanity. Thank you very much.